A modern robotic arm in motion has one operational purpose: moving a tool to a precise location to interact with an object. This is a schematic of a Planar 3R robot. It relies on 3 independent, motor-driven revolute joints. Between these joints are 2 primary rigid links, measuring 3 units and 2 units in length. Before the arm moves, we establish a baseline. When the arm straightens out perfectly horizontally along the x-axis, it sits in what is called the 0 configuration. At this exact position, all 3 joint angles, theta 1, theta 2, and theta 3, are precisely 0 degrees. Now, introduce an object into the workspace that the arm needs to grab. We can define this object's location using exact Cartesian coordinates, 3 units along the x-axis and 1 unit up the y-axis. But reaching the correct spatial location is only part of the problem. A gripper must also approach the object from the correct angle. For this specific task, the end effector requires a target orientation of -90 degrees. To understand that angle, compare the end effector's moving frame to the fixed base frame. Counterclockwise is positive and clockwise is negative. A -90-degree orientation means the gripper frame rotated exactly 90 degrees clockwise relative to the base. If we knew the angles of the 3 motors and wanted to calculate where the gripper ended up, we would use forward kinematics. Inverse kinematics poses the exact opposite problem. Knowing the final pose we want, we must calculate the specific joint angles required to reach it. Systematic control of these joints requires us to reverse the forward kinematics model through a rigorous 6-step analytical derivation. Translating a physical location into specific, executable motor commands means transforming geographic coordinates into a highly coupled system of nonlinear mathematical equations. Step 1 begins by writing out the forward kinematics using homogeneous transformation matrices. Here are 3 4x4 matrices, H1, H2, and H3. Each encapsulates a joint's rotational and translational displacement. By multiplying them together, they merge into a single resultant matrix representing the entire arm's state. For step 2, we formulate a system of equations by extracting specific variables directly out of this combined matrix. First, the matrice's rotational elements represent the end effector's overall orientation, the sum of theta 1, 2, and 3. Next, the final column's translation terms dictate Cartesian x and y locations, giving 2 distinct positional expressions. We set these extracted terms equal to our target variables, an x of 3, a y of 1, and an orientation of -90 degrees. This extraction process fundamentally maps the physical arm to a complex system of 3 nonlinear equations with 3 unknown variables. The x and y equations are highly coupled. Unknown joint angles are trapped inside identical sine and cosine functions, making them impossible to solve independently. To isolate variables, we stack the equations, square both sides, and add them together. This exploits the Pythagorean identity, sine squared plus cosine squared equals 1, stripping out complex variables. The polynomial condenses perfectly, 18 cosine theta 1 plus 6 sine theta 1 equals 15. Rigorous algebraic reduction is a mandatory preliminary step. You cannot solve for individual motor commands until the joint parameters are fully isolated from one another. Even in this simplified state, theta 1 cannot be isolated using basic algebraic moves. In step 4, trigonometric substitution, we divide every term by the square root of 18 squared plus 6 squared. Mapping these fractional coefficients onto a right-angle triangle introduces a known angle, gamma. We substitute the equation's coefficients for gamma's cosine and sine. With gamma in place, we move to step 5, solving the equation to find our multiple angle solutions. Substituting gamma triggers a mathematical property that collapses the left side into a single cosine function, allowing us to finally isolate theta 1. Executing an inverse cosine inherently generates both a positive and a negative result. There is no single answer. This plus-minus symbol physically splits the math into divergent branches. Branch A yields 56.2 degrees, while branch B yields -19.3 degrees. Because theta 1 is now a known constant, the variables in the remaining positional and orientation equations are no longer trapped. Substituting these 2 divergent theta 1 values back into our system generates 2 completely different sets of parameters for theta 2 and theta 3. Because the underlying kinematics rely on cyclical trigonometric functions, a single Cartesian target will almost always yield a multiplicity of valid mathematical states. This brings us to the final phase, evaluating physical viability by testing both derived mathematical solutions. Let's look at the parameters for solution A. Theta 1 sits at 56.2 degrees, theta 2 at negative 104.5, and theta 3 at negative 41.7. On the left, we watch this map to a smooth, real-world rotation that successfully places the gripper exactly where we wanted. Now consider solution B, where theta 1 is negative 19.3, theta 2 is 104.5, and theta 3 is negative 175.2. Mathematically, these angles perfectly satisfy the exact same target coordinates and orientation, but watch the right side of the screen. Achieving this pose requires the robot's rigid links to pass through its own base and intersect the solid floor of the workspace. The mathematics didn't fail. Algebraic equations exist in a purely theoretical space. They possess no inherent understanding of solid geometry, physical volume, or collision boundaries. To get a robot to reliably grab an object, you have to execute the full 6-step algorithmic process. You write the forward kinematic matrices, extract the equations, algebraically reduce them, apply trigonometric substitution, calculate the bifurcated angles, and evaluate the physical constraints. The algebraic process of inverse kinematics is mathematically powerful, but it is entirely blind to the real world. It must always be paired with a rigorous physical constraint analysis to guarantee operational safety on the factory floor.